welcome to this module, and in this module what we will be learning is how to deposit gold pad on the piezoresistive sensors that we have seen in the last module, and over the gold pad we will see how we can pattern SU8 pillars and make them conductive. So, if you remember in the last module we have seen, if you see the screen, oxidized silicon wafer, contact pad, piezoresistive material, silicon dioxide on the contact pad, right, SiO2, SiO2, silicon, SiO2, contact pad, piezoresistive material pattern to form piezoresistive sensor, right. This SiO2 we have used PECVD, this SiO2 we have used thermal oxidation, silicon wafer we know, chrome gold we have used physical vapor deposition. You can use E beam or thermal evaporation or sputtering, SPUTTERIN, sputtering, right. So, now let us see how can we deposit gold pad on the piezoresistive sensor, and the gold pad, if I deposit gold directly on the piezoresistive sensor, it will be shorted. That is why we have this insulating material, right. So, on this I will deposit gold. Now, this is in reality, right. So, I will just draw one single smooth line so that we do not get confused. This is my, so let me make circle for chrome gold. So, this is also my chrome gold, this is my chrome gold. So, the box with circle is chrome gold, the box with X is my silicon dioxide, which is PECVD, the box with dashed lines is silicon dioxide, LPCVD, right. And the box with dots is my piezoresistive material, clear. So, no confusion. So, what is this? I know it is chrome gold, right. Over chrome gold, what we have to do? We have to form gold pads, right. If you see the structure is like this. There is a piezoresistor, and on piezoresistor there is an insulator material or insulating material, right. On that what we will want? We want a gold pad, and then gold pad connection should come out, right. So, this is what we want. Now, insulating material, when I am drawing, insulating material is over all the places like this, except the contact region, right. So, insulating material is all the way on this everywhere like this, right. Now, we are having a gold pad and we are patterning the gold pad on this insulating material, and the contact of the gold pad will come on the insulator without shorting the contact of the piezoresistive material, and it will come like this. Okay. So, this two are for the piezoresistor, this for the gold pad, easy. So, now we have to pattern this gold pad, right, over the insulating material. So, that is why we have first deposited gold everywhere, right. First we have deposited gold using PVD, right. Now, when I say gold, you have to understand it is a chrome gold, because a thin layer of chrome is required to improve the adhesion, right. Now, on this what we will do, the next step is spin coat photoresist, spin coat photoresist, spin coating photoresist. Let us use this pattern for the photoresist. So, this one is my positive photoresist. Now, what I have to do? I have to have a gold pad, right, cross section. If I take a cross section of this, right, so I have to first have a mask, correct. Let us have a mask, and I want to only save this area. I only want to have or save this much area of chrome gold and etch the remaining area, and etch the remaining area. This is my bright field mask, bright field mask. Now, what I will do next is I will go for UV lithography, right. I will go for UV lithography. This is UV lithography, right. When I expose my wafer with UV lithography and I dip this wafer in photoresist developer, I dip this wafer in photoresist developer, what will happen? The unexposed area will be stronger and the exposed area will be weaker, correct. So, I will have my wafer oxide, again oxide, then gold material and photoresist will only be in this much area, right. This is after photoresist developer. After this, what is the next step? Next step is we will hard bake, right, hard bake. After hard baking, the next step is hard bake is done at 120 degree centigrade for 1 minute on hot plate. After this, what is the next step? Next step is we will etch chrome and gold, right. First we will dip in the chrome etchant or gold etchant. The first is we have to dip in the gold etchant, because chrome layer is below the gold layer, right. Chrome layer is below the gold layer. So, first we have to etch the gold layer. So, when we are saying etching chrome gold means first we will dip the wafer in gold etchant, then we will rinse the wafer with DI water, then we will dip the wafer in chrome etchant, then we will rinse the wafer in DI water, right, and then what will I have? I will have a pattern like this, right. Then after this what we will do? We will dip this wafer in acetone to strip up the photoresist. If I dip this wafer in acetone, what will happen? My photoresist will be stripped off and we will reach, let us say this is A, this is B, this is C, D, E and F. So, we have reached the F in the schematic diagram. Easy, very easy, right. So, I will etch it up. Now, is it etching? We are removing, right, we are rubbing it. Okay. So, this is F. Now, the next step is we have to pattern SU8 pillars on gold pad. We have to pattern SU8 pillars on gold pad, right. So, to do that our next step would be to spin coat SU8 on this wafer. Okay. If I spin coat SU8 on this wafer, then what is my next step? My next step is that I have to form the SU8 pillars, right. So, I have to first soft bake it. Soft bake is done at 65 degree centigrade for 1 minute on hot plate, right. This is my SU8, then soft bake 65 degree centigrade, right, not 1 minute, it depends on the thickness of SU8, right, thickness of SU8 on a hot plate or in a oven. So, time depends on thickness of SU8. This is already given in a data sheet. We do not have to remember 65 degree centigrade. What is the SU8 that we have to remember? What is the SU8? SU8 50, SU8 75. There are different kind of SU8 with last 2 digits SU8 50 for example, right. So, you have to see SU8 50 is what is the thickness that we get by spin coating on the using the spin coater, what is the thickness that we obtain. So, it is very important to understand the SU8 thickness, because based on that your soft bake time would be determined. After soft bake, we have to load the mask. We have to load the mask and it is a negative photoresist. We already know SU8 is a negative photoresist. So, we will use a dark field mask, because the unexposed region in the case of negative photoresist, this is our SU8. SU8 works as a negative photoresist. Okay. So, the unexposed region in the case of negative photoresist will be weaker, right. In the case of positive photoresist, what stronger, in the negative photoresist it will be weaker. So, when I expose this wafer with UV, what will happen? the unexposed region would be weaker and exposed region would be stronger. So, after UV exposure, what is the next step? In case of SU 8, hard bake, right? Hard bake is run as 95 degree centigrade. Again 95 degree centigrade is one point, but what is the time? Time depends on the thickness of the SU 8 material, right. After hard bake, we will develop the photoresist, that is your SU 8, by dipping the wafer in a SU 8 photoresist developer, right. So, if I dip this wafer in a SU 8 developer, what will happen? The SU 8 will remain only in this area, right, and then I can go for a further annealing at 120 or 140 degree centigrade to make the pillar harder. This is my SU 8 patterned, right, to form SU 8 pillar, right. Now, in principle we will make 8 different pillars, right. We will make 8 different pillars because our sensor demands 8 pillars. There are 8 electrodes and 8 piezoresistive sensors, right. So, we have reached, now we have reached E. Is it correct? See, A, B, C, D, E, F, E, no, A, B, C, D, E, F, G. So, we from F we have reached G. Okay. Now, what is the next step? We have to make SU 8 conductive, but can you make SU 8 conductive? We cannot make SU 8 conductive because SU 8 is a polymer. SU 8 is a non-conductive polymer. There are conductive polymer which we have just used for piezoresistive sensor, and that is your P dot PSS. P dot PSS is a piezoresistive, they can be used for piezoresistive sensor because it is a piezoresistive material and it is a conductive polymer. We are talking about SU 8 which is a non-conducting polymer. So, how can we make a non-conducting polymer conducting? We do not want to make a non-conducting polymer conducting, we want a thin layer of metal over SU 8 so that it can act as a channel to flow the electrons through it. So, or over it. Let me explain it to you in terms of schematic, so you understand it better, right. So, just if you can look at the screen. What after this, once I have a SU 8 pillar, right, once I have SU 8 pillar, I will put this wafer in a thermal evaporator at 45 degree angle. Generally wafers are at 90 degree angle, I will load it at 45 degree angle. So, there is a SU 8 pillar like this, right. What will happen when you evaporate the material, right, that is your, let us say, chrome and gold, the one side of the SU 8, the top layer of the SU 8 and one side of SU 8 will be coated with chrome gold, and what is this material? This material is already a chrome gold, this is also chrome gold, right. So, this will be conductive from here till here, right. We can have conductivity because it is a chrome gold, this layer is also chrome gold, we know it, see here written somewhere, no, chrome gold, right. So, using physical vapor deposition, we can, and by loading the wafer in a certain angle, we can coat single side of the chrome gold of the SU 8 pillar along with the top side, and thus we can make the conductive path, or we can have the conductive path on the SU 8 pillar. So, we will be here H, right, H. What is the next step? Next step is I, where you have to cut the PDMS and release it to realize the flexible MEMS based sensor, to realize the flexible MEMS based sensor. Got it, guys? So, once you have the flexible MEMS based sensor, what you will do with that? What you will do with that? So, we will see this thing in a next module. Let us finish this module right over here, because this is the end of the fabrication of a flexible MEMS based sensor, and in the next module what we will see is how can we use this sensor to test the tissue property, to measure the tissue properties. In particular, we are interested in mechanical properties and electrical properties, since we have piezoresistors and a conductive electrode. Right. Till then, you look at the lecture, and I'll get back to you in my next module with the application of this flexible sensor, right, which is integrated with two different sensing modalities. One is electrical and one is mechanical. Right. Till then, you take care. I'll see you in the next class. Bye.